Speed, endurance, and pace are top priorities for bike racers. To go as fast as possible, racers rely on gears, proportions, and ratios to get the most out of their bicycles. Uphill, downhill, and straightaway, a simple shift in gears and some legwork can make the difference between winning or staying behind. In mathematics, we're constantly looking for patterns or connections between values to help us understand the world we live in. Some patterns show direct relationships between quantities. That means if one value gets bigger, the other value gets bigger. And if one value gets smaller, the other value gets smaller. Like, the bigger your feet, the bigger your shoes. Or the more rain there is outside, the more umbrella sales there are. When the escalator goes down, I go down. Or when the escalator goes up, I go up. Some direct relationships between values are even more special. They form what's called a direct proportion. Here's proportional reasoning in action. This recipe calls for 2 eggs for every 1 cup of flour. When you're working with direct proportions, multiplying is the key to proportional relationships. So if I want to multiply the recipe by 2 to make a double batch, then I would need 2 times as many eggs. 4 eggs. And 2 times as much flour. 2 cups. If I'd want to triple the batch, I would need 3 times as many eggs. 6 eggs and 3 times as much flour. 3 cups. A quadruple batch means equal rates or equal ratios make direct proportions, create line graphs like this, and give great results. Give me 1 minute, and I can tell you about how many people are in this stadium. Since I don't have time to count everyone, one by one, then I'll use proportional reasoning. One section of the stadium has a capacity of 1,000 people. That's a rate of 1,000 people per one section. From there, a proportion will help us estimate how many people are in the whole stadium. If I know there are 75 sections, then I have 75 times as many people. We've got our proportion. 75 times 1,000 is an estimate of 75,000 people in the entire stadium. Population estimates are useful in another arena. Jason Eckstein is a wildlife biologist in this wilderness area. So Jason, why do you tag and put radio transmitters on deer?
Local deer population here is very high, and they're basically destroying the forest. They're eating everything in sight. And so we're looking at the home range of these animals and the habitats they're using. And with that, we'll be able to follow these deer around, see which areas they're using. And from that, we can tell the local land managers how they should better manage their deer herd to protect the forest. I use proportional reasoning all the time. For example, we have our aerial survey for our counts, and we have the area that I'm using. We have about 7 square miles of deer habitat here. So I take the number of deer I have per square mile, so we have about 75 deer per square mile. And that's our wintering population.
But since you've counted all the deer, a birthing season has come, so now you have more deer, and you use proportional reasoning to find the new population?
From our original survey that we have, we can say, for example, we have 300 does. And from these 300 does, we know that 70 out of 100 are going to have twins. So we have 210 of those does are going to have twins. We also know that 20 out of 100 are going to have singles. So we have 60 deer going to have singles. And we know that 10 out of 100 are going to have triplets. So we have 30 deer going to have triplets. We now have 570 fawns, plus our additional 500 animals we counted from our aerial survey. So our new population is now 1,070 white-tailed deer.
In this biochemistry lab, they go beyond estimating. Sumeda Gulati needs exact values as she dilutes a concentrated solution in her laboratory.
I have a 50 times concentrated solution, and I need to dilute it down to 1 times its concentration. So I take 49 parts of the diluting water and 1 part of this 50 times concentrated solution, and I mix the two up. The total volume that I need is 500 ml or 500 milliliter. So I will add 490 milliliter of water and 10 milliliter of the concentrated or 50 times concentrated solution. You have to be exact in terms of the volume you use so that you get an exact concentration for the amount of buffer you're going to make.
I've always wondered why the front tires of old bicycles were so big. Well, there was a good reason. Old-time bicyclists were interested in saving time and energy. They figured that the best use of their energy was to build a bike that traveled a long way for each turn of the pedal. You turn the pedal once around, and the wheel goes once around. So if it's a giant wheel, you'd go further down the road. A smart advantage, if you can climb up there without falling off. Let's shift gears and take a look at today's bikes. This bike is a compound machine made up of wheels, gears, and levers that work together to increase the force riders make with their leg muscles. A shift makes the chain move to a different gear with a different number of teeth. The number of teeth on the front gear compared to the number of teeth on the back gear is the gear ratio. For example, gear 1 on this bike connects the chain between 42 teeth on the front gear and 24 on the back gear. If we change that ratio to a decimal by dividing the first term by the second term, we get 1 75/100. That's the actual gear ratio in decimal fraction form. Look at another important ratio. As I turn the foot pedal around once, the bike wheel goes around 1 75/100 times. The ratio of turns of the bike wheel compared to turns of the foot pedal equals the gear ratio. The gear ratio equals the wheel-pedal ratio. That creates a proportion. Rich Karstensen races bikes and knows about ratios and proportions.
I usually choose the high gear. The advantage of the high gear is that the wheel travels more times around for every one time I pedal, and for every time that wheel goes around, I travel the circumference of that wheel. If you're riding up the hills, you would want to choose a lower gear to where it would pedal, or your pedal rotations would move a lot easier.
And it would be more efficient, right?
It would be much more efficient. You would save energy.
But what if I was going downhill?
Going down the hills, you would want to shift into a higher gear to where it would pedal much harder and your wheel rotations would go much quicker though. Flat ground, once again, you would probably stay in a higher gear that would be energy efficient to where you would be pedaling within 90 to 120 RPMs. Basically, when I first start a race, the excitement's there, but yet you want to be efficient with your pedal strokes. For instance, I would pedal really easy at the first start of the race to get my legs warmed up. As the race goes on, you start to work, your legs start to tire, and some of the race might pick up to where you have to pedal in some harder gears. And as the race ends, for instance, you would want to use probably your hardest gear for your sprint finish. The most fun I've ever had in a race is being at the finish line racing with 5 or 6 different guys and coming out of the pack and winning the race.
It seems that bikes and proportions are a winning team. Proportional reasoning is an important mathematical tool. We can reduce a numerically big picture or blow up a tiny picture into something we can imagine. It helps us make sense of whatever it is we're thinking about. Think about comparing the populations of different states. The United States has about 300 million people. I can't even begin to picture that many people or compare the populations of different states. So let's shrink the numbers down into something I can imagine, like 1/1,000,000th as many people. That's 300 people in the US. Instead of the 17 million people in Texas, I'll picture it as 17 people living in that state, 30 people in California, and half a person in South Dakota. We just proportionally shrunk some big numbers. How about blowing up something very small? What if I'm trying to compare the size of a bacteria to the size of a virus? Without a microscope, I can't see a bacteria or a virus. How could I imagine their comparison? Picture this toy car next to this sedan, enlarging both the virus and the bacteria about 1 million times. That's a picture I can handle. Multiplication is the key to thinking proportionally. 1 million times one term of the ratio means 1 million times the other term of the ratio to stay in proportion. But there's another multiplication connection for proportions. Suppose 2 out of every 3 people in a crowd are wearing sunglasses. At that same ratio, how many people would be wearing sunglasses in a crowd of 12? This is a proportion with a missing value. By cross-multiplying the terms like this, I can change the proportion to an equation like this, do some multiplying and dividing, and find the missing value in the proportion. In a direct relationship between two numbers, when one value goes up, the other value goes up. And when one value goes down, the other value goes down. In a direct relationship that's a direct proportion, both values change by the same multiplication factor. But not all direct relationships are direct proportions. Take the two temperature scales, Fahrenheit and Celsius. When the temperature rises, the reading in the Fahrenheit scale rises and the reading in the Celsius scale rises. I can see the linear pattern between the two temperature readings on a graph. 10 degrees Celsius is equivalent to 50 degrees Fahrenheit. 20 degrees Celsius equals 68 degrees Fahrenheit. But if I double the Celsius reading, that doesn't mean I just double the Fahrenheit reading for a certain temperature. It's a direct relationship, but not a direct proportion. So when you're planning your next vacation, you better pay attention to which scale on the thermometer you're reading. So not all direct relationships are direct proportions. And not all relationships between amounts are even direct relationships. Some relationships are more like seesaws than escalators. When one value goes up, the other value goes down. That makes it an inverse relationship instead of a direct relationship. And check this out. If one person weighs twice as much as the other, the heavier person needs to be half as far from the pivot point in order to be balanced. In other words, the more weight you have, the closer you need to be to the pivot. Here's another inverse relationship. The faster a rider goes, the less time it takes to finish a race. Understanding relationships between numbers, particularly understanding proportional reasoning, can be really powerful. Proportional reasoning is a tool of mathematics that can help you estimate when you can't count the exact numbers, calculate when you need to win, and picture things that you can't imagine. With proportional reasoning in your toolbox, you'll never be left out of the winner's circle.